Here we have two angles, angle alpha and angle beta, and they've given us two trigonometric functions, ratios for those, a sine for alpha and a sine of beta. And we're going to do the following. So this is the process we're going to do. We're going to first set up a triangle with alpha. So here is a triangle for alpha, a right triangle. Try to draw the best you can as a right triangle. Here's angle alpha. Recall that sine is opposite over hypotenuse. So the opposite in this case will be 3 and the hypotenuse will be 5. The hypotenuse being the longest side of the right triangle, opposite of the right angle. At the end of this triangle, it would be nice for us to not only give the sine, but also give the cosine of alpha. So we already know the sine of alpha is 3 over 5. Let's see what the cosine would be. So we're going to go ahead and find the missing side using the Pythagorean theorem. 5 squared minus 3 squared. That's 25 minus 9. That's 16, and square root of 16 is 4. So the missing side is 4. So the opposite would be 4. Cosine would be the adjacent, opposite is 3, adjacent is 4. So the adjacent would be 4, and the hypotenuse would be 5. We're going to do the same thing again, though, for the beta. Here's beta. Opposite will be 5, hypotenuse will be 13. This missing side, we will do 13 squared minus 5 squared. 169 minus 25. That's 144, and the square root of 144 is 12. So the missing side is 12. In a similar manner, we're going to set up sine of beta is 5 over 13. Cosine of beta, in this case, is 12 over 13. So keep in mind that we have two sets of trig ratios for two different angles. I have this first set right here, and I have the second set right here. After that is done, we're going to go ahead and find sine alpha plus beta. So sine alpha plus beta, I'm going to plug in these numbers in these parentheses. Sine of alpha was 3 over 5. Cosine of alpha was 4 over 5. Cosine beta ended up being 12 over 13. And the sine was 5 over 13. So we can only get to this point if we have set the setups for the two right triangles and found sine and cosine for both. And now we simplify. So we have 3 times 12 is 36. 5 times 13 is 65. 4 times 5 is 20. They are a common denominator. We're lucky. This ends up becoming 56 over 65. So what we're saying is that sine of alpha plus beta is exactly equal to 56 over 65. So the formula for this is going to be different, right? It's cosine alpha plus beta. Don't forget that it has a minus in the formula. Hopefully you did that right. We're going to use the same values we got from before, all right? We substituted the 4 over 5 for cosine alpha, the 12 over 13 for cosine beta, etc. We simplify. 48 over 65 minus 15 over 65 results in 33 over 65. Now, this is what's so fascinating. Remember that for the sine up here, we got a positive answer, 56 over 65. And for the cosine, we're getting a positive answer of 33 over 65. So in what quadrant is the angle alpha plus beta? Well, we can know what quadrant it's in based on the signs of the sine and the cosine. So in what quadrant is sine and cosine positive at the same time? Well, only in quadrant 1. Okay. If, for example, sine was positive, but cosine was negative, then it would be in quadrant 2, etc. Okay, but in this problem, our sine answer was positive, our cosine answer was positive, both of them were positive, therefore it was in quadrant 1. You'll see these proofs aren't really that bad. For the most case, it's simply substituting and then simplifying. So let's see what happens with this little proof here. Show that this left side is this right side, and of course, we always pick the uglier side first. If you recall, the formula for sine of x plus y, the formula for sine x minus y, you'll note that these two are the same terms, and these two are the same terms. However, I hope you notice that this is a positive cosine sign. This is a minus cosine sign, so these two cancel each other out. We have these two right here. These two are left. These two, these two, these two are left. Hint, these two are left. I'm going to combine them. It looked ugly. It was a pretty straightforward proof. Done. What would a problem like problem 6 end up in quadrant 2, or in quadrant 3, or for that matter in quadrant 4? Because remember, problem 6, alpha plus beta ended up in quadrant 1 because both the sine and the cosine were positive. So take a moment to reflect on when would a problem like problem 6 end up in quadrant 2, quadrant 3, or quadrant 4. So with the addition and subtraction formulas, we're taking two different angles, two different angles from two different triangles, and seeing if we can add or subtract. Okay, so we're taking a 30-degree and a 45-degree. We want to add those up to a 75-degree and see what the actual results are. Now we're going to switch our focus to double angle formula. So this time we're looking at just one angle. We're going to double it. So if we do give you 45 degrees and we double it, we get 90 degrees. Does it behave the same way as if we just thought of a 90-degree angle? Well, let's go ahead and first show you. We're going to prove these formulas from the addition formula. So let's assume that alpha is beta. Okay, so we're going to do the addition. Instead of beta, I'm going to put another alpha. So if I add those two up, I get 2 alpha. Now, let's see what happens with the formulas themselves. So we get sine of alpha times cosine of alpha plus cosine of alpha times sine of alpha, right? Because instead of the betas, I put alphas for all of them now. But what you'll notice is that if I flip these around, I get the same thing as this first term. So what I end up getting is a sine of 2 alpha is 2 sine alpha cosine alpha. This is our first double angle formula. This is the same thing to find cosine of 2 alpha. So cosine of 2 alpha would be the same if I let alpha is equal to beta. So in other words, it's going to be alpha plus alpha. So we have cosine of alpha plus alpha. I'm just replacing the beta with an alpha. So I have 2 of them now, 1, 2. And this ends up being cosine alpha. Remember that if it's addition for cosine, it's a minus. Remember, all the betas have been changed to alphas. So I get cosine 2 alpha. The double angle of a cosine is going to be cosine squared alpha minus sine squared alpha. Now your brain is doing some weird stuff right now. It's thinking, this looks vaguely familiar, but it looks a little off. Yeah, because it probably reminds you of the Pythagorean identity. However, the Pythagorean identity was a plus, not a minus. So as much as you want to think this is the Pythagorean identity, it's not. Okay, but this is the double angle for a formula for cosine. If we were to take that and recall the Pythagorean identity was that sine squared plus cosine squared is equal to 1. And from this we get two things. If I get the sine squared by itself, I get 1 minus cosine squared alpha. If I want to get the cosine squared by itself, it ends up being 1 minus sine squared alpha. Keep those in mind. So if I take, for example, the original one, cosine 2 alpha is cosine squared alpha minus sine squared alpha, right? What we just found in problem 8. And instead, we replaced, let's say, sine squared. Sine squared is 1 minus cosine squared. We get cosine squared alpha minus 1 plus cosine squared alpha, right? You distribute this negative. We can combine these like terms. Those are 2 of them. So I get cosine of 2 alpha is equal to 2 cosine squared alpha minus 1. That's another possible way to represent the cosine double angle formula. Why would we even bother with this? Well, because this actually makes life easy. If all you have is cosine, then all you do is plug it in and you're done. Okay, the first equation that we found originally required you to have both sine and cosine. Now, what if we did this again, but this time we did it for, instead of substituting for the sine, we substitute for the cosine. Recall cosine squared over here is 1 minus sine squared. And so what we get is this setup. There's two of these and they're both negative. And we get this representation. Here I summarize for you the 3 for cosine. Okay, these if you need the double angle the cosine of a double angle, you can use any one of these 3. When do you know which one to use? Well, for example, if you have sine, use this one because all you need is sine. If all they give you was cosine, use this one. If they end up giving you both of them, you might as well go ahead and go all the way with this one. Okay? Food for thought.